Thank you so much to the organizers for putting this together and for the kind invitation. So I'm going to talk about the shape of math to come. I don't know if you recognize the title. Of course, I'm referring to Ornette Coleman, the shape of jazz to come. But let's get into it a little bit. If maybe you don't like jazz, but yeah. So I don't know if this is. I thought of it as Yogi Berra, but I looked it up, and apparently Niels Bohr maybe said it, or some old Danish proverb that prediction is difficult, especially about the future. So instead of trying to look forward, let's first look backwards. What did people say? And there was a really interesting meeting in Tel Aviv in 1999 that was published in the Proceedings of GAFA in the year 2000. And it's all these talks are on YouTube. Yeah, all these talks are on YouTube, but the talks are great too, but then there's actually proceedings where you can read, the details of what people say, this visions in mathematics, and a lot of really, really interesting things here. I strongly encourage, just in general, to read this. Gromov has some very, everybody, there's lots of contributions, Eli Stein, Yasha Sinai, Bergan, anyway. So the one that I'm going to focus in on is by Tim Gowers, and the title might not seem like it's something that's about the future. It's about rough structure and classification, and in fact, that rough structure and classification he only gets to in section 3 of this paper, and it's what we would now call approximate structures. So the work that happened in the decade after is exactly what he predicted was going to be happening in this one article, and lots of field medals came out of it. The Green-Tau theorem, and more the stronger theorem, the inverse theorem for Gowers norms, that there are no non-approximate nil sequences, the sum product theorem, that there are no non-approximate rings, the triple product, and maybe building up to Briard-Green-Tau, that there are no non-approximate groups in general. So I realize this is maybe not, well, the audience maybe doesn't know all these things, so I'm not going to say anything about these at all, except to say that the ideas that Gowers was talking about in this paper were extremely prescient, but the part that I will focus in on is section 2 of this paper, which says, will mathematics exist in the year 2099? Okay, so this is in the year 1999, looking to the millennium, or we don't have to look that far ahead, let's just look in the century. And what's that? Will people exist? Yeah.
Chapter 1.
Okay, chapter 1, will people exist? That's true. Assuming people exist, will mathematics exist? And so I was going to divide this into 4 categories of discovery of new mathematics. Just because you discovered it doesn't mean you really understand it, even if you can prove it. So do we understand mathematics? How do we communicate that mathematics to other professional mathematicians? And teaching, the difference between teaching and communication is teaching is communicating mathematics to people who are new to mathematics as opposed to people who are already professionals. And then I realized I can't actually tell the difference between understanding and communication. So these became sort of one category. I think that those are basically synonymous as far as I can tell. Okay, so let's jump right in with discovery. So I just grabbed a paragraph out of Gowers' paper. Let me return to the question of automating mathematics and present an imagined dialogue between a mathematician and computer in 2 or 3 decades' time. So he's spot on, okay? 2025. And here's what the discussion is. So the mathematician says, is the following true? If you have a positive proportion, if you have a subset of the positive proportion of the natural numbers, do you find a 3-term progression? And the computer says, well, anyway, there's a whole discussion like this. And this is the early, for me, I don't know, maybe there's an earlier form of this where someone really nailed what it will look like to talk to a chatbot 25 years out. And this is the earliest prompt engineering that I could find that's really looks like modern. And this is from the year 2000, okay, quarter century ago. Let me just continue with this paragraph. I have written the dialogue in English, but it's supposed to be a translation. It turns out, no, you can actually talk to it in English, but it's supposed to be a translation of a more formal language, which has not yet been invented. So again, he's seeing things in the future. But let me jump back. The idea is that the dialogue with the computer is helpful, but it's not doing anything particularly clever. So let me zoom in a little bit on that. Let me insult all of your intelligence by saying what I mean by an LLM. for 1 second, because I want to really define terms and get to the nitty gritty. It's like in a math talk, I'm going to define what the natural numbers are, just so we're all on the same page. So apologies for this. I think of it as, my mind as an LLM, and I'm reading to the bottom of book, and I'm flipping. Remember, there used to be these things. It wasn't just you click a button on your iPhone or Kindle. You actually turn the page and you fumble, and your brain can't help. There's an LLM inside your brain, and it can't help but autocomplete. And so you're reading, Harry didn't even know what all the Horcruxes were. Meanwhile, he was at a loss to know how to what? Maybe how to destroy the Horcruxes, or how to find the Horcruxes, or how to sandwich, maybe sandwich is the next word. Okay, so then you ask every human being alive, and 20% of them might say destroy, and 7% of them might say find, and almost nobody would say sandwich. And so this is like, an LLM to me is a game of Family Feud. Survey says, except survey is all of written language ever. Okay, so that's at its core. It's a function. Just really, really abstractly, I'm taking out all of the amazing engineering that goes into the existence of such things. Jared?
Yeah, also to be clear, so like I think Family Feud is a great example. So the contestants are not saying what they think the next word should be. They're saying what they think the community would say is the next word.
That's right. That's right. And what I really want is, I want to specify that an LLM, a lot of people confuse LLMs and chatbots, and I'm sure I'll say the word LLM when I actually mean a chatbot. An LLM is just a model. It's a function from context to distribution of next tokens, okay, as opposed to the choice of the next token. So what I have in mind for Family Feud is that the answer board is the LLM, not what the contestant is doing. The contestant is more like the chatbot, where the contestant is saying, I think this is the most likely next word. Does that make sense? So the fact that the answer key has 20% of people saying find and 7% saying, destroy or something.
I thought that would be more of the distribution, and then
the distribution is the model of language. It's a function from context to a distribution of next tokens. That's exactly why I want to make this point.
So you're saying the chatbots are the contestants?
Chatbot, exactly. The chatbot as contestant lives on top of the model, and now you have to decide: are you going to take the most likely? This is what temperature does. You say how much into the distribution do you want to sample to make things a little bit more interesting. Okay, so I really want to distinguish the existence of this function, however it comes about, however you train it, however the engineering, whatever H100 farm you have somewhere that's running it, whatever GPUs and CPUs, GPUs really. And the main point I want to make about chatbots, so again, a chatbot will decide, given the context, what that next token should be, add that next token to the context, and just iterate that until the token says, stop talking, right? That's just so that we're all on the same page of what's going on. And so this chatbot, which again, I and many others will confuse with the word LLM, is stochastic. Stochastic doesn't just mean random. It's randomness on top of randomness on top of randomness, because every time you make a choice of what that word is, you add it to the context and you run it again. And so it really is compounding randomness, the way Brownian motion compounds randomness after every instant of time. Okay, and so this stochasticity, I claim, is both its power and weakness, and there's a vital difference between stochastic processes and deterministic processes. There's no, if you choose the wrong word in the middle of a Edgar Allan Poe poem, or in the middle of Ornette Coleman jazz solo, you stick a blue note in there somewhere, you can still have an amazing jazz solo. You can still recover and have an incredible product at the end. If you get a theorem 99% right and there's just one minus sign missing somewhere in the middle, that's a useless thing, right? It could be completely wrong. It might be useful. It might be useful. There might be very useful ideas that you can recover, but it might be utterly useless. And there was a minus sign at the very beginning that ruins the entire argument. Okay, so theorems are deterministic in a way that poetry and language in general and jazz solos are stochastic. Okay, I want to separate these. And this really, to me, feels there's a strong analogy between that and Danny Kahneman's. I mean, it's not, Danny Kahneman popularized this way of thinking about what the human brain seems to have as these two different modes of thought, system one and system two. System one is, if I ask you 3 + 8, you guys aren't counting, my little ones might be counting on their fingers, but at this point, for you all, it's effortless. Whereas, okay, maybe for some of you, 437 times 82, you can answer instantaneously. I would have to get out a piece of paper and do a calculation. Okay, so system 2 is slow, calculating, kind of infrequent. And so when I do 437 times 82, actually what maybe the purpose of school is to start with, school math is to start with things that are system 2 and convert them to processes involving chains of system 1. Right? So when I do 432 times 82, I know how to set it up so that I'm doing a whole bunch of system 1 processes that are, I know what 2 times 7 is. I know to put the 4 there and the 1, I'll save for later and so on. And so system 2 is really a long chain of system 1. Okay? And so if you think about it, if we have some process that takes 1,000 steps, where every step you have a 99% chance of success, but success requires every single one of them to be right. What are the odds, what probability do you have of succeeding in the end? And of course, it's minuscule, okay? So, but chatbots don't have to be pure LLMs. They can use tools, right? It's not that you have to answer. I mean, there are people who try to train chatbots to do multiplication table in language. I don't understand why, because the way that I got this 0.004 is I asked Claude, what is 0.99 to the 1,000? And it said, I'll figure it out, but I'm not going to guess in language what it is. I'll write a JavaScript, I'll run that JavaScript, and that'll get me the answer, and there it is. Right? So this is the beauty of tools, Elliot.
I don't think there should be a percentage sign, though.
No, I took 2 zeros off. I multiplied it by 100, didn't I? Anyway, we can discuss later. I think I got it right, but maybe not. Okay, so when these chatbots use tools, they can, despite the fact that all they're doing is producing next tokens, they can then do deterministic things with those next tokens, like run a JavaScript. Yeah.
So if you really know you only want to take 1,000 steps, if your model is big enough, it's been trained on enough data, and you lower the temperature enough.
I'm coming to that. Yeah, that's the bitter lesson. Yeah, I'm coming to that. Okay, so chatbots can use tools. Oh, but let me give you a caveat about using those tools. So DeepMind, I was at the Institute on sabbatical last year, and DeepMind stopped by and visited us, and they were showing us all kinds of great things. And one of the talks was an example where they were using Gemini, and they wanted to compute the genus of some curve, and Gemini was trained to write the corresponding Sage code that calls Sage, and it says this is genus 1, but they know it's genus 2. Like, is there a bug in Sage? How is this happening? And so the way it's happening is that there's a safety feature that turns off call Sage, and it was turned off. And the LLM was trained to call Sage, but it couldn't. So it just pretended that it called Sage and answered in natural language whatever it thought the answer was supposed to be. Okay, so whenever I work in these things, I should have taken this JavaScript for 0.99 to the 1,000, run it locally on my machine, gotten that answer, and not trusted the AI to report it, because, anyway, the LLMs are not trustworthy. All right, never mind. So if what we're trying to do is reason about mathematics, then the tool that you want to reach for is obvious. It's an interactive theorem prover, a proof assistant. These have a very long history, and I will, just like I'll confuse LLMs with chatbots, I'll confuse interactive theorem provers with Lean, because Lean is the one that's sort of exploding in the mathematical community. And Lean itself means lots of different things. So let me try to define what I mean by that. So I see sort of 4 big areas where Lean is involved. The core is this was software to make bug-free code. It had nothing to do with proving theorems. The fact that it does prove theorems is kind of a sideshow, or at least it was originally. Then on top of that, people built this massive, beautifully synthesized, interconnected library, because if you want to do algebraic groups, you need the manifolds library, you need the groups library, you need the algebraic geometry library, and all these things have to talk to one another. They can't just be built completely independently and then hope that when you import all of them, there's no crash across everything. So this is a really, really important bit of engineering without which you basically can't get started. If I have to literally define the natural numbers in order to get to, you know, some cohomological computation, we're going to be in trouble. We're not going to get anywhere. So let me just zoom in on MATLib 4 a little bit, because when I tell my pure math number theory friends, oh, MATLib is this amazing thing, they open up a page of MATLib, they can't understand a word that's in there, and they say, what is this nonsense? I'm an expert in this subject. They're telling me they're proving some basic things here, and I don't understand a word. And MATLib is not an educational project. It is not there for you to learn math, for you to learn how to do this math formally. It's not there to learn how to write lean. It's just to get to from 1 million or 2 million lines of code to 10 million lines of code to 100 million lines of code and still be able to do everything. And so there's all this golfing and compression that is required in order to be able to go from these different scales and still be able to do math interactively. Once it takes 3 minutes for lean to, if you write one line of lean and it takes 3 minutes, which is not that long in the grand scheme of things, but if that's how long it takes for it to respond and tell you, yes, I understand this line of code or not, it's done as being interactive, right? So it's really, really important that this engineering is done right. Okay, so I'll come back to teaching later. Let's talk about research. And on top of MATLib, the hope, the vision is that mathematicians will eventually be able to do actual research. And this was and remains sort of my motivation. Really, what I was frustrated by is analytic number theory. I mean, this was kind of, this is nowhere near the worst equation in one of my papers, but it's one that could fit on a slide while still being ugly enough to get the point across. You know, we have these 100-page technical papers with lots of calculations. One minus sign kills the entire argument. Everything falls apart. And we have calculators that keep track of arithmetic. Why can't a computer keep track of my minus signs? And the answer is it can. You just, that's what lean does for you. Okay, so the only reason I got involved in formalization is I want to do math. But I see that math will be easier in the world where there's enough formalization for me to be able to work formally from the beginning. Unfortunately, so at the moment, I can't even state a single one of my theorems formally in lean. And that's because I need the library to be several orders of magnitude larger to get there. Math grows at some, our creation of new mathematics grows at some exponent, our creation of new formalization grows at some other exponent, and the formalization exponent is less than the mathematics exponent. Okay? So it will never catch up unless we hook up formalization to something else, to something even more powerful to help it catch up. Okay, so I want to do math, but you know, I want to do it formally because I think that'll speed up my math workflow, but it's not going to get there unless we supercharge that with something else, and now we get to AI. Okay, so this is sort of, at least in my world, I'm trying to recurse back up to math, but I'm sort of stuck going down and down into these realms. Okay, does that make sense? So, so let's talk about that automation. And this is, to me, kind of, once I understood this picture, I understood what I think things are going to look like soon. That's the claim. So if you think about how mathematicians talk to one another, communicate with one another, give talks, and write their papers. We don't write our papers even here. This informal is the wrong term. It's just the one that could fit on the slide. What I really mean there is natural language. But we don't write our papers really with natural language statements. What we really work is at the level of ideas, even though we claim to be here. We really, you know, because L1 is controlled by L2 in a compact space, you yada yada. There's a theorem there, which is like Cauchy-Schwarz or something, but at professional levels, the way things are written are not nearly as decomposed as they would need to be in order to continue the rest of this process. Nevertheless, so this is where I want to work. That's the level at which I want to understand things, because it's not just, my goal isn't just to get things formalized or to prove theorems, it's to understand. And I understand at a different scale than the scale at which you have to prove things, you know, and get everything exactly right. So what I would like is you take my paper, and an LLM will break down the big statements into much smaller pieces, this decomposition into bite-sized pieces, filling in all kinds of little details in natural language. So in natural language, you give me a formal natural language statement of what was informally stated in natural language, and then give me sort of the main steps in the proof. The reason I call this quasi-autoformalization and not autoformalization is that at every stage, I don't need this to be automatically done by a machine. As long as I'm happy to intervene if I'm going to get these constants the other way around, right? And formalization eventually is fast enough that it can catch up to the pace at which new mathematics is created. Even so, where's Jared? There. So even with Gauss, this decomposition step was done by a human and interactively, right? I'm sorry I missed I was teaching during your lecture, and so I don't know what I'm allowed to say or not allowed to say.
So just as a maybe great point as an announcement, so Drew allowed us, we're gonna give a same talk on Thursday at MIT, so if you're around.
Yeah, at 2:30, if I remember correctly. Yeah.
219.
So, but my point is that even this part was done interactively with a human being, and it's just at the final step, whatever wasn't working, whatever the AI couldn't close on the formal side, you would decompose even further. The human being would decompose even further, and then you try again. And so it's still iterative. And of course, the eventual idea is get the human out of every single step of it, and you can just work at the level of ideas. Okay, so again, quasi-autoformalization is that I don't mind intervening as long as it's moving things faster than I can type individual tactics or look up theorem names in the library and things like that, which is how formalization currently works. So that's why it's quasi-autoformalization. Once we've decomposed this in natural language sufficiently, then I would like another LLM. Maybe, I mean, it doesn't have to be. The point is these are different jobs. So maybe you want to special train different systems that do these jobs. Then you want to train an LLM that takes the informal statement, turns it into a formal statement in Lean, takes every proof step and scaffolds the formal statement into various proof steps that don't need to necessarily be proved completely at this stage. Just at the end, you check that you've scaffolded it so much that yes, Lean will accept that scaffold as a proof of the formal statement. Okay. Now the danger here is that translation is difficult. It's difficult enough for human beings to do this translation and get it right and not make mistakes and find where the mistakes are. So just a few examples of this. So there's this DeepMind formal conjectures project. Now conjectures are even trickier than theorems because you're not providing a proof. So you really don't know if you've stated things correctly or not. I decided to run an experiment, so I open up Claude and I say, tell me about the Bateman-Horn conjecture. It gives me, it's read Wikipedia. This is all in Wikipedia, so it just gives me the statement. And then I say, okay, so then help me formalize this statement in Lean 4, use as much built-in API that MATLAB already has developed. And it nearly perfectly one-shots. This is just completely automatically generated. How should I say what this local factor that's a product of primes, what's the right way to phrase that? I don't need to learn any of this syntax anymore to generate the syntax. I do need to learn the syntax to understand what it's given, because it turns out that when you look at this a little bit more closely, there are serious issues with what it proposed as the formalization. It got a whole bunch of things wrong. You would never know that it got it wrong because you're not trying to prove the statement. But even if you give a statement and its proof formally, you still don't know if the definitions were formalized correctly, if the statement was formalized exactly as you mean it to be, okay? So my kind of view on this is that the human is responsible for any claims that the human makes, whatever tools they use to come up with those claims. All right, so I would not want to, where was it? I would not want at this stage just to look away and say, oh yeah, the AI gave me a certificate that it got it. And so I think my theorem's right. No, I will hold myself responsible for making sure that the formal statement and the definitions are exactly right. The proofs I can allow Lean to check for me. I still want to understand what's going on at the end of the day, but down to that level, I'll let Lean do the checking. Okay, does that make sense? A second example, so there's lots of examples of this nature. Let me just give you a second one, which came up in a really lovely paper of David Loeffler and Michael Stahl, who formalized zeta and L functions in Lean in the math library. So let me remind you or tell you or just throw a picture up that the people say the Riemann zeta function is summation 1 over n to the s. That's like the Euler or Bernoulli zeta function. The whole reason it has Riemann's name on it is because he realized what you do is you take a theta function, take its Mellin transform, divide by gammas, and so this is how you get the proper Riemann zeta function. And then the Riemann hypothesis says that if zeta is 0, and okay, there's these trivial zeros with real part of s less than a negative real part, then all the zeros lie on the 1/2 line. And there's a subtle thing that happens with this version of the zeta function that the Riemann hypothesis might have been false, as stated, because, well, let me go back, because the way formalization works, you don't have functions on restricted domains. So the zeta function in lean is a function on the entire complex plane. And what is its value at 1? The value at 1 is just some junk value. It just goes there so that you can evaluate it everywhere. And it could have been 0. So that's what they point out here. So this is in the paper. The junk value at 1, however it propagated through these definitions, could have turned out to be 0. And then you turn on some AI and in a trillion lines that says, I've solved the Riemann hypothesis for you. It's actually false. Yeah. And there's a 0 off the line. And you have to figure out, oh, that 0 off the line is that s equals 1. And the reason is because you didn't handle this triviality, what mathematically seems like a triviality, you didn't handle it properly.
How is it defining the Riemann hypothesis to avoid the actual trivial zeros? Like if you just say there are no non-real zeros, etc., well, one happens to be on the real axis too.
That's true. You could just define, you could change your definition. So again, making the statements precise, formalizing statements is difficult. So your version of the Riemann hypothesis is there are no, any non-real zeros on the imaginary line. I mean, on the central line, on the 1/2 line, on the critical line. Sure. The whole point of this section is that translating what we think of as obvious mathematical facts into actual literal formal mathematical statements has some subtlety to it. So I agree. Okay, so a counterpoint. So I was talking to Christian Zegedy about this, and he says, don't you believe in mathematics? Don't you believe in the robustness of mathematics? If you get something wrong, if you get some statement wrong, if you get some definition wrong, the definition is what it is for a reason. You're trying to do something with it. When you go to do something with it, you'll immediately notice that it's doing the wrong thing. Either you're proving things that you don't want to be true, or you're stuck in sort of, you're unable to make progress. So the definitions are what they are and the theorem statements are what they are because they do what you want them to do. And if not, so if you auto-formalize a statement by mistake, either it wasn't that important and then you won't know the difference, but it doesn't do anything. Or if it is important, you'll eventually realize that you made a mistake and you have to, go back and refactor how you were doing things. And in natural, not in natural language, when human beings do formalization, they do this all the time. The notion of groups was refactored 5 times or something in MathLib to the version that currently exists there. Okay, so Christian says, in the long term, mathematics will be right because you'll eventually error correct until you get the definition that works in practice, because you'll be doing it in practice. So don't worry about it so much if you get the formalization wrong the first 3 times. Okay.
I think that's contrary to your point about the exponent being larger. That error correction requires on the human exponent, which is the mathematics is growing faster than the mathematics we can correct, we can notice errors in. And so that means that the majority of mathematics will always have mistakes in it where we haven't noticed the errors.
I agree. But why can't an automated process look for those errors and correct it as quickly as?
Specifically talking about errors of human formalizing the wrong statement. It's not a problem in formalization.
Well, okay, I'm saying several things. Humans can make the wrong formalization. AI can make the wrong formalization. When we, not just if, but when we make these mistakes, we, over time, realize them, and then we have to go back and refactor and do it all again. So you're saying that's going to force delta to go below.
I'm just if we're relying on humans.
No, I want to hear.
I just think, I mean, you can make the same argument that we don't need any of this automation because humans will eventually find all the typos in all the analyst papers that exist because eventually the right person will read it and realize that there's an error.
But in practice, that is what happens, right?
It is. But your argument, sort of counter, I mean, you want things formalized, but the frustration is that mathematics is growing at a rate faster than we can error correct. And I think that still applies here.
I think that one of the missing points is just in practice, the speed at which automation is increasing. So it's not necessarily the current capability of an agent right now, but looking forward, at least maybe 5 years ago, the rate of an agent couldn't do anything, and then 5 years from now, thinking about just maybe you have like a further exponent that you're tracking. It's not the current capabilities of an agent, but the kind of the rate at which these errors can be identified and handled. Maybe that has its own exponent.
Yeah, I guess I'm including all of the things that go into mathematics in general into each of those exponents. So part of mathematics is you're reading a paper and you realize this lemma is actually wrong and the lemma ruins the whole paper. And now I have to write a paper, correcting what's here. And that's just a part of mathematical growth. Epsilon doesn't mean that we're necessarily always making positive progress. Sometimes we have to backtrack and fix something that is in the literature and is wrong. And the same thing will happen whether you're doing it in natural language or formally. Yes?
So I'm very curious about so you're saying that the translation is going to be more and more right, but do you think there's a point where it's completely right? And if so, what would make the transition from converging to being right to being right?
It's a great question. I don't know how to tell. I don't know if I will ever be at a place where I can tell that we're right. I mean, calculus was done for a long time by Euler. Every paper written by Euler did not have an epsilon and delta in it. And then at some point in the 19th century, Fourier comes along and sort of ruins everything for us, or Cauchy. And all of a sudden, by the end of the 19th century, we need epsilons and deltas. And then we realized actually topology doesn't have to be about metric spaces. It could just be an abstract topology. So we found a better way to do it. And then actually you shouldn't be doing even topology. If you want to do limits, you just need filters. And so we keep discovering new ways, new and better ways of doing things. So I don't think it's ever, as a mathematician, I would never say this is the final correct answer. We're constantly looking for better ways of doing things, and we're constantly looking to improve our methods and discover more truth in more efficient ways. It's a process. It's the journey, not the destination. I don't know if that applies. Yes.
I mean, I think that from how I read this whole point, it's that whatever is formalized is correct, right? And then I think that as far as the translation goes, the translation is sort of, it's proximus in some sort of space to the formalization. And maybe that mirrors in some ways, to your point, this process of I tried to prove this thing and then I couldn't, and so I'm going to weaken this hypothesis.
I agree. I would say that discussion is already present in natural language mathematics. You're trying to prove something, you don't know how to do it, so you prove some related thing or some subcase, or that's just a natural part of mathematical growth. For me, the issue is my theorem has a meaning to me. And when I translate that theorem formally, the meaning might change. I might have to phrase it in some other way. I might have to talk about non-real zeros of the zeta function as opposed to zeros in the critical strip. Or some subtle things like this that I think are the same, but I actually have to check. So this is the semantic versus syntax. Lean will check that the proof, whatever it is that's being claimed, is correct. Is what's being claimed, is the meaning of what's being claimed, what I think the meaning is in natural language. That's the point I'm trying to make. So these things are really subtle. Yeah. Okay, let me try to move along. So yes, so this is a step that I foresee some difficulty with in making sure that what we think we're proving formally, when Lean checks, yes, you've proved it formally, is that really what you intended it to say? Does it have exactly the same meaning or not? Okay, and then of course the final step is you have all these, you've scaffolded things, but that's not the proof. You have to fill in all the sorries, and so this is where you bring in your closer, I allowed to say Yankees when I'm in Boston? Mariano Rivera or something? Okay, so, yeah, okay. So once a problem is sufficiently scaffolded, then you bring in alpha proof or Gödel prover or Gauss or whoever and let it fill in these sorries. So just to, I haven't had a chance to play with Gauss, but again, when the DeepMind folks visited, so Thomas Hubert came to my office and we got to play a little bit with alpha proof. And so I was just blown away by the kind of proofs that alpha proof can produce. Because, so I wrote this first line, zeta blows up. At some point I needed to know that the zeta function is, it blows up at 1. So in a neighborhood of 1, not including 1, it should be, an absolute value greater than 1. And what string of characters do I have to put into lean so that it will agree with me? And it turns out this is, well, I don't know if it's the shortest, but it's a sufficient string of characters. And this, from line 2 all the way down to line 30, was automatically produced by alpha proof. Okay, so when I saw this, I said, okay, we're here. We've arrived. I can just say what I want to say with a have. There's a sorry. The sorry, it's in the library somewhere. You have to put together the right pieces in the right way. And I don't have to think about it. I don't have to worry about it because I know what this means. And this means what I think it means. And now I don't need to look at this. Lean says it's okay. And as far as I'm concerned, it's okay. Okay, so I was really, really impressed. If you think about, again, I forget who asked the question, maybe about chaining 1,000, chaining 1,000, what the right next token is in a sequence. That's it, and it's done. So we're there in a sense. Okay, this took 2 minutes to respond, which I didn't have to leave it running overnight. I certainly didn't leave it running for a week. And they did one extra little engineering thing that I really appreciated, which was while those 2 minutes were happening, I could keep working in other parts of the file, which is an important thing to have because that's not how a lot of the tactics in Lean work. So, okay, that's just a small aside. Okay, so again, so the upshot of this whole discussion is that to me, this is the greatest short-term challenge, getting this flowchart working. In a sense, not only are we sort of within range, maybe we're already here. So you put together, alpha proof or Gödel prover or Gauss. What I don't know is how resource intensive is. I know how resource intensive Claude is because I pay them $20 a month, and then I can do all of this with Claude, and it's not as good as, it does not spit out 30 lines of dense lean code that proves kind of statements that they're not trivial, but they're certainly not hard for a professional mathematician. So I don't know, they haven't asked me for $20 a month and let me just, go to town with their servers. But it's coming. It's coming. This, if it's not here already, it's very, very not far away. Okay. So, well, you do all this work and you say, did you really need the formalization? Why, it's awful lot of resources. LLMs are getting really, really good. Can't we just do math in natural language? We've been doing it for 3,000 years. And okay, you have this 1,000 steps, each of which has a 99% chance. You're not gonna be able to scale everything together. But look, reasoning models are really, really successful. At the 2023 IMO, I don't think a single AI got a single point, which is the median score for high schoolers as well. So is that right? I don't remember. Something like that. Okay, so in 2024, alpha proof was the only thing to get, they got a silver medal. It's not just they got, they were 1 point off of the gold medal. And then, you fast forward 1 year and DeepMind says, actually, we didn't need that formalization. We can do it purely in LLM. Purely in next token. It's not just next token. There's a reasoning model. It talks to itself. It computes for days at a time. But they went from using formalization in 2024 to not using formalization in 2025. Just Gemini can still get a gold medal on the IMO. Okay, so do we really need this? Well, a couple of things. First of all, my prediction for how many AI systems will get a gold in July 2026 is 0. Because by then it'll no longer be a useful benchmark for any of them. They won't even bother competing. Okay, they'll be so far. I mean, professional mathematicians don't do the IMO, right? So in the same way, like we went from nobody could do it, then one person can do it, then like, you know, a handful can do it, and then nobody bothers to do it because it's just too easy. We'll see. And so given that, won't we eventually be able to do all of math in natural language? Why all this effort? Well, I don't know if these numbers are right, but I think the number of raw steps that you do from advanced high school math to advanced undergraduate math is something like on the order of, I don't know, 100 or 1,000-fold jumps in that system 2 things converting to system 1. Your brain can skip that many levels from undergraduate math to graduate level math is another order of magnitude from what graduate students do to what a postdoc can do is another order of magnitude. And then from that to, you know, math professors, and from that to Brigance, I sort of, you know, if you like chess analogies, you know, a GM might be like a math PhD, but then a 2500 GM and a 2600 GM is a completely different thing. That's like a postdoc versus a 2700, which is, you know, a professional mathematician versus Magnus Carlsen, you know, a world champion kind of mathematician. So these are, again, people who can skip, whose system 1 is orders of magnitude more adapt. So things that are system 2 for a professional mathematician would be system 1 for Jean. Okay, he just skips ahead and says, here's the answer to this calculation. And that's why he can do so many things. He can see so much farther. Please, and I just guessed 1,000. Is that? Okay. So you'll tell me what? Yeah, this was not scientific, and I'm glad to hear that. It seems like something someone would have studied. So, but so, you know, what's that? Do you agree? I mean, does it feel to you like there's orders of magnitude in what you skip, in what you can skip over, what you can do automatically from undergrad to grad to postdoc to professional level? You don't agree. Interesting.
Actually, some of them.
1,000 was because I had 1,000 up there. Okay, so 10.
Well, it's 1,000 steps that you might
There
have
exists a
taken,
constancy.
summarized in
Yeah.
build your thoughts correctly. The main point is that the 1,000 steps are summarized.
Exactly.
Yeah.
Well, that is what I'm saying. That those steps.
That's right. So the 1,000 shouldn't be in your slide. It should be the summary. Yes.
I guess I should say.
Well, let's come back to it because obviously there's discussion.
Okay.
Yeah.
Let's come back to it. But the point is, you know, yeah, we've managed to do this, the 1,000 steps that it takes for high school level, but then we have to go several orders of magnitude more before we get, you know, Jean Brigand style AI. And of course, there's the bitter lesson that plus Moore's law that can we eventually get these chains to continue? And you might say, you know, it's improbable. On the other hand, in practice, that is what happens. And that's the bitter lesson. You try to do something more clever and someone with more compute just does better than you without doing anything more clever. Just more compute.
But comparison with chess, I mean, every, you know, club level player knows what the rules of chess are. I'm not even sure that an undergraduate mathematician would be able to understand all of the, I mean, we have this whole lecture series coming for the $1 million questions, and you know, most undergraduates won't understand half of these.
I think both analogies need some work. So I'm workshopping them here, and I'd be happy to. There are tactical strategies that a 2700 GM sees that would be difficult for a 2500 to follow. Would you agree with that?
Sure.
That's the analogy I'm trying to make. Yeah.
A little bit of Jan lecture yesterday where he talks about these different systems, and as you move upwards, the information within the lower level is kind of thought of as like entropy. When you think of these like higher level mathematical constructs that develop as you move deeper into your career, you can imagine that those constructs, you know, once they're formalized into lean, then you can move with them as kind of like these big modular blocks of constructs. Everything beneath that, you know, that has not been proved yet would still need that more granular level. So probably a much longer chain of steps. But then there's sort of this gap every time you build a new level of construct between what the LLM is capable of understanding via its training set in order to formalize it.
Yeah, that's a really good point. I wasn't going to talk about it here, but elsewhere I spoke about the fact that we're sort of, as mathematicians, it's like you want to build a rocket, but you're going to create every single part for that rocket yourself. You're going to mine the ore and melt it down and machine this part and put it together. And the age of formalization, you could just buy a part off the shelf and not worry that you're not using it correctly because it's completely specified down to the exact parameters of how it works. So I do see that in the future, we'll be able to build much, much bigger rockets than we can today because we'll be able to rely much more systematically on work of others that once things are formalized. So yeah, Elliot.
I think that the advance that got all these AI labs the IMO gold medal was like, it's not that their per step accuracy has gone to like 99.9% or whatever is needed, but rather I think they have gained the ability to like look back at previous tokens and say, oh, I see an error there, and cross that out and try again. Sort of the way when any of us think about problems, we all have a lot of very flawed steps in our head. It's just that there's another layer that we do before actually attempting to write down a proof.
Exactly, yeah. And they talk to themselves and say, wait a second, that doesn't seem right. You know, I think there's an error here, or yeah, there's these long reasoning chains and the ability to remove something that was there previously. There are a lot of things going, and half of them were pure LLM, and another half were formal also. So people are kind of playing both games. But the point I wanted to make is that here's an even better, or maybe worse reason to insist on formalization. Like maybe LLMs can do all of this. Maybe I'm wrong to speak about formalization. But let's imagine a world where Gemini or Claude or whoever can produce 100 math papers a day in natural language, and let's say it's 99% accurate. So 99 of those papers are perfect new theorems contributing to our knowledge of the universe, and one of them has a minus sign error. I would not use that tool at all. That tool would be utterly useless to me because I don't know which one. And I have to sit there and sift through these 99 papers, checking them by hand to make sure that I'm not quoting one of the theorems that's wrong. Okay, so the fact that you can generate lots and lots of mathematics and have it be really nearly correct is just not good enough. I would not use this. I would find this tool amazing if it existed. Look at what it can do. I would mine it for ideas, for things that I'm trying to prove, but it's not reliable. If 99 of those papers are perfectly correct, but I don't know which one is the one that's wrong, I can't use any of them.
What's the error rate on the archive?
Yeah.
I'm sure this is better than the error rate on the archive. You're absolutely right. Mathematicians do much worse than this, but what's that?
We should be formalizing our proof anyway.
That's coming. Yeah, I think in the future we will be. It's yeah.
But it seems to me like you would want to use the tool just because.
To mine it for ideas, but I really don't want to be.
You wouldn't trust it.
I wouldn't trust it, and so if I wanted one of those papers, I'd have to sit there and myself check that the paper is right before I'd be willing to use it. Then I'm no worse or better off than how things currently are.
You have a proof that says like if either X or Y is true, then I have proven conjecture Z, and X and Y are two different papers.
I like that. Yeah. Of course, you don't know if in this particular batch you got two papers wrong. All right. So anyway, so this is what I mean by actually theoretically, I don't want a tool that's purely language based. If I'm going to use these systems to help me do my research, I actually want them to be formalized. Period. Even if it can do everything that it wants to do in natural language. Okay, so so the upshot about discovery, is that right? That's 10 to 1. Okay, the upshot in discovery, in the future, MathLib, I mean, it already is a big and robust library. It's going to be orders of magnitude bigger if it's engineered correctly. By the way, I didn't talk about this, but that alpha proof cannot go into MathLib. You will not survive a library that is full of 30-line gobbledygook things. So we need some other AI that's a refactor AI that goes through and takes that gobbledygook proof and turns it into 3 lines, which is what it should be to prove that theorem correctly. That's what should go into the library because we need that library to be engineered to go to 10 million and 100 million lines of code. Jared?
Yeah, I mean, just as a interpretation, in mathematical history, one of the great refactorers of our time was Grothendieck.
Grothendieck.
He brought to bear the language of abstract algebra, sheaves and schemes, and then ported it and unified these loose analogies across classical algebraic geometry and then arithmetic geometry. But yeah, like some sort of unification like that would be.
Yeah, this is less about unification because I think of that as big ideas and more about cleaning up. Like someone had a party and proved the theorem, but now you need to mop up what's been done and make it actually something usable to go into the library. Like the library cannot grow. I don't think the library can grow to the size that it needs to grow to be useful if we allow alpha proof type. I didn't look at what Gauss puts out, but I'm guessing it's kind of like alpha proof. I haven't seen a system that puts out beautiful one-line, mathlib quality.
Different categories. I mean, the present situation would be there's only annals of mathematics, and every paper has to meet that standard, which is really not viable.
Absolutely, absolutely. Yeah.
Can you just say more? I don't understand why the 30-line gobbledygook is not sufficient. It compiles. All you care is that the theorem is true.
The amount of time it takes for it to compile. If the entire library, just add 20% to the library as it currently exists, then when you go to use it, when you're doing things like something in algebraic geometry, something in the Fermat-Last theorem repository, it will start to take 3 minutes. For the
Practical concern about
it's an engineering. It's absolutely just an engineering issue.
It's a cache.
It's cached, but the more you have things like this, yeah, mathlib needs to be clean.
It's not just like you want it to be beautiful. Like there's an actual.
Yeah.
I also want it to be beautiful, but I also, more importantly, need it to work at long chains of reasoning and building on top of very large structures, far from the axioms. True.
The good news is this problem is not at all specific to mathematics. This is a problem for all of automated coding everywhere when you're describing software engineering of a large software library. Every line of code you add to it adds maintenance costs. You want to try to minimize that. You want to make sure you're reusing code. And all the companies that are using all these automated coding tools are facing the exact same problem. Hopefully they'll solve it for us.
Yeah, I agree completely. So the hope is that eventually, like right now, if I were to even try to prove one of my theorems, I would first prove it on paper, write the paper, put it on the archive, send it to a journal, and then I would say, okay, can I actually formalize this? And I'd try to work within the theorem prover. I want to reverse that process. I want it to be so fast at doing mathematics in lean so that I don't have to think, I have these 30 lemmas with some exponential sum bounds, and I'm gonna go over them 3 times each to make sure I didn't miss a minus sign somewhere. Instead, not only do I put it in to lean myself, an AI puts it in, I look and I say, yep, that's the theorem I wanted to say, it does what I want it to, it's gonna speed up my workflow. I want to speed up my workflow. My time is the most valuable resource that I have. So the point where working formally is faster than working on paper is the point where everybody is you don't have to coerce anybody. You don't have to say this journal only accepts formalized proofs. Journals will do that, I believe, but you don't have to wait for that. What people call, the constant, what's that? Oh, sorry.
We're editors of a journal. Talking about how nice.
Okay, wait.
Study the crank with exactly this suggestion formalized proof. Serious.
Yeah. Every call-outs thing I get. Well, I don't respond to them anymore because there's too many of them. But
this was a credible person, but who was really frustrated that their elementary proof of FLT couldn't get published anywhere. And I said, the only way you're ever going to get this anywhere is to formalize it. You've already got a framed up blueprint you can use.
Exactly. Yeah. And if you believe that you really did this and it would be a huge achievement, invest the time. Yeah, and then people will listen.
People would take it seriously.
Yeah. So people had talked, De Bruyn sort of named this constant, which is the ratio in the number of lines of formal code. How much work do you have to do extra in lines of code relative to the natural language proof? And I claim that's the wrong ratio. Because I don't care how many lines this thing produces. LLMs can produce lots and lots of lines of code. I care about my time. So it's the right metric is, I claim, is the time to formalize a paper in lean and letting the kernel check correctness as opposed to the time it takes to typeset it in tech and write it by hand and recheck every lemma again and again until I'm satisfied with it. That's the metric that I think the instant that metric gets below 1, through great efficient libraries that are engineered so that they work, automation, great tactics in those libraries, and the use of all the automation in LLMs and so on. And making, if you want to use Lean right now, maybe there's an online server, live, leanlang.org, but it's like, my students don't even download TechShop to their computers anymore. They just open up Overleaf, and boom, they have it working. That's the kind of things. Those are the kinds of things that need to happen so that everyone will voluntarily switch to working formally because it's just easier. There's no point in you don't have to coerce anybody. You just it's faster, and this is what people will want to do. Let me make one remark about journals. Just because it's formalized, I had this experience when I was editor-in-chief of Experimental Math, and we ran a special issue on formalization, and everything submitted to that special issue was formalized. Came with, it was a paper that explained what was going on. It came with a formalization in Lean and Isabelle and Coq and so on. And I thought, this is going to be amazing. It's going to revolutionize publication. You just, send it to an expert. The expert looks at it and says, looks good. Let it in, and that's it. There is no part 2 of, check every line and make sure it's right. That's wrong. That's wrong, because you still have to check that the formalization means what you think it means. And in fact, there was an issue where formalization didn't mean what people thought it meant. And so, again, that problem is hard. You still need referees. You still need people that check for correctness. Yes, it will be much easier than it is today, but it's not a solved problem. The volume will make up for whatever problems are solved will be filled up with the fact that the volume will increase, and we'll be back to the same problems. Okay, so editors of journals, sorry, it's not gonna solve all our problems. Okay, let's see. Well, maybe it's good that the clicker died because I'm probably out of time. Oh, there we are. I was going to talk about teaching. I think I won't talk about teaching. I think let's get some lunch. I'll stop there. Thank you.